You guys, you have to go just by what I say. All right, more about the gradient. So just a recap of some of the important ideas that we came up with yesterday. And then we'll jump in to our new material. Because this is really the first really new idea that we've talked about really all year long. So the important idea is directional derivative. Directional derivative, the rate of change of the function in an arbitrary direction. So the directional derivative tells us how our function is changing as we move in some arbitrary direction. And our arbitrary direction is given by some unit vector. So that's what the directional derivative is. In developing the idea of the directional derivative, we came up with a compact way of writing it. And we talked about the del operator. You'll also, the del operator is also called nabla. And we define the del operator as d dxi plus d dy j, and if we had a three variable function, or if we're working with more variables, we'd have a plus d dz. Okay, so I'll just put that in parentheses. And we said that the del operator has to operate on something to have any meaning. It has to operate on a function, and later on we'll use the del operator and we'll operate on vectors. But it has to operate on something to have a meaning. It doesn't have any value on its own. The gradient. So the gradient of, and we talked about the gradient of a function z equals f of xy. We said that del f is dz dxi plus dz dy j. dz, why did I write two z's here? I was thinking if there was a z, we'd have a ddz. So this is our gradient, and we said that you'll also sometimes see it. It's an older notation. You'll see it written as grad f. Del f and grad f mean the same thing. And if we have a unit vector AB, where our length is 1, that the directional derivative in the direction of u of f was del f dot u. So this gives us a compact way of writing our directional derivative using the gradient. Right at the end of class yesterday, we talked about some properties of the gradient. We said that if del f equals 0, the gradient of the function equals 0, then the directional derivative is 0 everywhere for any unit vector. Our second property of the gradient was that del f gives the maximum gives a direction of the maximum directional derivative. And the magnitude of the maximum directional derivative was just the magnitude of the gradient. So that gives us our direction of our maximum directional derivative, and the magnitude of the maximum directional derivative is the magnitude of the gradient. And the minimum directional derivative is just in the opposite direction, and the minimum magnitude is the negative of this magnitude. So I wanted to show you quickly why these properties are true. Very, very easy to show why the properties are true. So we'll go through that very quickly, and then we'll talk about some other properties of the gradient that are going to be very, very useful for us. So these are our important ideas from yesterday. So proof. We're going to proof of properties. So the first one, we said if del f equals 0, then the directional derivative of f equals 0 for all unit vectors. Well, we know that the directional derivative is del f dot u, and it follows immediately if del f is 0, and this should be a vector. If del f is a 0 vector, then the dot product is going to be 0 with any vector. So that one's easy. If our gradient is 0, then our directional derivative has to be 0 everywhere. So what would you guess? Just thinking about what we're talking about here. If the gradient is 0, what is that telling you about your function, your surface? Not changing. So what kind of shape would it be? A plane. It'd be flat, right? There's no the function's not changing. The gradient is not changing. Or so you're talking about some kind of flat surface. There's no gradient. It's not changing. All right, property 2. We said the maximum directional derivative was in the direction of the gradient. The gradient gives us the maximum directional derivative. So for number 2, let phi be the angle between del f and our unit vector. And we're going to remember that this nice property of the dot product, del f dot u, is the magnitude of del f times the magnitude of u times the cosine of the angle between them. And we know that u is a unit vector, so the magnitude of u is 1. So del f dot u is just the magnitude of del f times the cosine of phi. Well, what is cosine? Cosine of phi is going to vary between what two values? Negative 1 and 1. So the directional derivative is going to be maximum when cosine phi equals So the directional derivative del f dot u is going to be maximum when the cosine has its maximum value. So this is going to be a max when cosine phi is a max. So cosine phi has to be what? What's the maximum of the cosine? 1. So phi has to be 0. So this is going to be maximum when the unit vector, when we're traveling in the direction of the gradient. The angle between our unit vector and our gradient is 0. And the magnitude of that maximum directional derivative is just going to be the magnitude of del f, because the cosine of 0 is 1. So that property follows directly from this. What's going to be the minimum value of del f dot u? When cosine takes on what value? When the cosine is negative 1. So it's going to be a minimum when cosine phi equals negative 1. So phi equals pi. So that tells us that for the minimum value, the unit vector and the gradient point in the opposite directions. So the minimum value of the directional derivative is in the opposite direction of the gradient. And the magnitude is, since our directional derivative is just del f cosine phi, the minimum magnitude is going to be negative magnitude of del f. So those properties come from using the properties of the dot product to look at this. So the directional derivative points in the direction of the maximum rate of change of f, and the opposite of that direction is the minimum rate of change of f. So the compass heading that the gradient gives you will be the steepest route up the hill, and you going the opposite direction would be the steepest route, the most steep route downhill, so the opposite. All right, questions on the properties? So let's look at another important property of the gradient. And this came up a little bit in your homework. You did a homework problem that had to do with this. So let's look at a level curve of a function. So another important property. So we're going to look at a level curve of f. So we're just looking in the plane now. And we're going to look at one level curve, a portion of a level curve. So here's my portion of my level curve. And what do we know about z on a level curve? And this could be we're not, so it could be in the xy plane, but if we're not in the xy plane, if we're on a level curve somewhere else, z is a constant. On a level curve, z equals constant. So I'm going to, now we're going to draw a unit tangent vector to the level curve. So let's draw a unit tangent vector here. right here at this point. So this is a unit tangent vector to our level curve at this point. So since we're on the level curve, what is the directional derivative in the direction of u going to be? Does it go, so we're on the level curve. So we're thinking about the directional derivative, the rate of change of f in the direction of this unit tangent vector on this level curve. So if z is a constant, what's the rate of change? If we're on that level curve, how much is z changing?
0.
None, right? So what's our directional derivative going to be?
0.
0. Our directional derivative is going to be 0 because z is constant. We know that the directional derivative is del f dot u, and that is 0. If the dot product is 0, what does that tell us about the angle between del f and u?
That is 5.2.
90 degrees. They're orthogonal. So since z is some arbitrary function, u is an arbitrary unit tangent vector, if we're on a level curve, del f, the gradient, and the unit tangent vector are orthogonal, so del f is orthogonal to the level curve. So for any function, so this is going to be our theorem. So we're going to say so, and our condition is if f is differentiable, at some point, and we want del f not to be 0 there. Because if del f is 0, then if our gradient is 0, then our directional derivative is 0 no matter what. Then del f at that particular point, at x0, y0, is normal to the level curve through that point. So the gradient of a function is normal to the level curves of the function. And this is going to be important when we talk about a 3-variable function, because when we start talking about surfaces, it turns out that our gradient is normal to the surface. So that will give us a normal vector to our surface. So this is kind of the two-dimensional version of that. So our gradient is normal to level curves of our function. That's going to be an important property of our gradient. Questions on this particular idea? So we have lots of ideas. We're making lots of connections with the gradient. The gradient gives us our maximum rate of change, our maximum directional derivative. It gives us our minimum directional derivative. Our gradient is normal to level curves. Our gradient, if we take the dot product with a unit vector, it gives us the directional derivative in that direction. So the gradient is a really important tool that we're going to be using really for the rest of the year. All right, let's do a couple of examples. We'll get to do one of my favorite examples, one of my favorite problems that we do in the entire chapter today. So we'll do a couple of examples and we'll be done. So we're gonna start out with an easy one. We're gonna say f of xy equals xy. We want to find a normal vector to the level curve of f of xy equals 3 at -1, 3. So we have this surface. We're talking about a level curve when f of xy equals 3, and we want a normal vector to that level curve. So we have xy equals 3. So this is f of xy equals a constant. And we know that del f, the gradient, is normal to level curves. So del f is going to be what for this particular function? yi plus xj. Partial with respect to x times I hat plus a partial with respect to y times j hat. So at our point, our gradient, del f, is 3i minus j. So there's our normal vector. So that vector is going to be normal to the level curve f of xy equals 3 at the point -1, 3. Pretty easy, right? That's it.
That's your favorite problem?
No, the next one's my favorite
Oh,
problem.
okay. I was like, woo!
Yeah. So we're going to use this idea next to solve a more interesting problem. And this next one is my favorite problem one of my favorite problems of the chapter.
Do you have like a favorite problem of like everything we do in this class ever?
My favorite problem ever is going to be in chapter 15. Where we get to find the volume. We get to find the volume of an ice cream cone with a scoop of ice cream on top. And we get to use spherical coordinates. We get to use triple integrals. It's really nice. All right. So for this example, we have this function t of xy. T of xy equals 100 minus x squared minus 2y squared. This function gives the temperature at any point on a metal plate. So we figured out how the temperature varies on this metal plate. We want to find the path of a heat-seeking particle at the point 4, 3. So this is my favorite problem of I think one of my favorite problems of chapter 13. So, any ideas how we're gonna approach this?
When it changes, like there's both like six or something.
It has to do with, so it's
The
heat
max
seeking.
value.
So Cole came up with a good guess. He says the gradient. We're talking about the gradient, so that's going to be a good guess. But the gradient has to do with
Is that the max?
the maximum increase. So if it's heat seeking, it's going to be moving in the direction where the temperature is maximum, right? So it's going to have to do with the gradient. If I make a sketch of this, so if we sketch the level curves of this, just looking at this function, what are the level curves going to look like? Ellipse. These are going to be ellipses. So 2x squared, 2y squared plus x squared equals some number. That's going to give us an ellipse. So we're going to have ellipses in the xy plane. So if I make a quick sketch of the level curves, just so.
Do we only look at the XY plane?
So the level curves are z equals constant,
Oh, just
right? So we'd set this equal to a constant and we get ellipses. So we end up with ellipses that have their major axis horizontal, and I know my ellipses aren't perfect. So we get something like this. And our particle, we know that it's going to move in the direction of the maximum temperature. So relative to these level curves, what's the path going to look like relative to these level curves? The gradient is perpendicular, normal to the level curves. So at any point, it's going to go perpendicular to the level curve. So our path is going to look something like, here it'll be perpendicular, here it'll be perpendicular, here it'll be perpendicular. So it kind of curves. It's going to have some kind of curving path. And I know my lines aren't exactly perpendicular to it, but it's going to have some kind of curving path towards the maximum temperature. So the gradient is going to point in the direction of the maximum temperature. So del T so if I wrote this, if I say we have some constant equals 100 minus x squared minus 2y squared. If I switch everything x's and y's to the side, so I have x squared plus 2y squared equals some other constant, C1. Divide everything by 2. I get x squared over 2 plus y squared equals some other constant. And does that make sense? Okay. Right. So del T is in the direction of the maximum temperature increase. So that's going to be part of our problem. So del T, the gradient of our temperature, is going to be what's going to be our gradient? Minus 2x I minus 4yj. So that gives us something to work with. We want the path. So if we're talking about the path, we're talking about some position vector. So let's say r of t, our position vector, our position as a function of time, is just some function x of ti plus y of t j. So this is our position vector. So we have our gradient. We know our gradient points in the direction of the maximum temperature increase. Here's our position vector. We need to find some kind of expression for this position vector, some kind of path. Well, what other vector quantity is going to point in the direction that this particle is moving? So just thinking of a position vector. What vector quantity that we've been working with points in the direction that the particle is moving? What, a unit vector? What?
The thing that's
T?
I don't remember.
What's T stand for?
The principal.
The tangent vector.
Tangent vector.
So a tangent vector is going to point in the direction that's moving. What gives us a tangent vector from R? R prime is going to be tangent to our path. That's going to point in the direction of motion. So R prime points in the direction of motion. It's a tangent vector. R prime of t is, and I'm just going to write it as derivatives, dx dt I plus dy dt j also points in the direction of motion. It's moving in this direction, and this is also in the direction of motion. So these two vectors, r prime and del t, are pointing in the same direction, so what can we say about them? They're scalar multiples. So yes, del t, Cole says, are they pointing in the same direction? Del t points in the direction of maximum temperature increase. We want the particle, the path of the particle moving in that direction, and r prime points in the direction that the particle is moving. So what did you say, Katie?
They're scalar multiples.
Scalar multiples. Del t and r prime are going to be scalar multiples. They're parallel. They're pointing in the same direction. So we're going to say del t equals some scalar multiple, and I'm going to write it the other direction. R prime is some scalar multiple of del t. So I can say, I'm just going to write this equation in terms of our expressions here. So minus 2xi and it doesn't matter which side I put the constant on. I put the constant here. It could be on the other side. So I'm going to say minus 2xi minus 4yj equals some constant. I know I switched it around here. Some constant times dx dt I plus some constant times dy dt j. Now I have a differential equation in the x component and a differential equation in the y component.
So we're doing this basically because we need like the actual value to attach the del operator to.
Right. So we need some kind of quantity, and we also need a quantity to relate it to the direction of motion. So the direction, we want the path. So it has something to do with the position of the particle. So we want to get some kind of relationship between the direction of motion, and we know that the gradient points in that direction. So we have to come up with some kind of relationship. All right, so equating components, we're going to say that minus 2x equals c dx dt, and minus 4y equals c dy dt. I'm going to solve each of these for dt. So c times dx over 2x equals dt, and that equals c times dy over 4y, or negative 4y. So I solve each of these for dt, and now I can equate these two, and I have a relationship between x and y. Is everybody with me before I switch pages? There should be a negative here, yes. So I have these, I equated components, solved each of these for dt. Now I have a relationship between x and y. All right, we good? So we can say that to dx over x equals dy over y. So I just simplified that last equation that we came up with, and I get 2 dx over x equals dy over y. Solve this differential equation. I have x's on one side and y's on the other side. I can just integrate both sides. So 2 natural log x plus natural log y, sorry, should be equals natural log y plus a constant, some constant. We know that the particle starts at 4, 3. That was our initial condition. How can I rewrite this? How can I rewrite this expression? Is it 2x? X squared equals, I'm going to say C2 times y. So I just rewrite this in exponential form. C2 is e to the C1. So this equation becomes x squared equals C2y. Use my initial condition. So 16 equals C2 times 3, and I get C2 equals 16 thirds. And plugging this back in here, so 16 thirds y equals x squared. Solve for y, I get y equals 3/16 x squared. And that's our path of our particle.
How do we know the path of the particle though?
It's
Well,
going in the direction of that.
right, we know it goes in the direction of maximum temperature increase. So del T points in the direction of maximum temperature increase. We came up with some arbitrary vector for the position vector, RT, and we knew that R prime of T also points in the same direction as the maximum temperature increase. So because the gradient gives us our maximum temperature increase, we were able to set up that relationship between the gradient and the velocity vector. So this particle, heat-seeking particle on a plate, one of my favorite problems in the entire chapter. Any questions? All right, homework. So the homework should make more sense now, Eric.